This conference will now be recorded.
All right, we can start right on time. It is 4 o'clock now here in South Africa. And from our presenters, wait a second, I'll share my screen. I am Andrea Bianchini speaking. I hope that everyone is here well. And if you please just remember to keep the microphone on mute so that the presenter doesn't have background noises, and eventually switch off the camera. All right. So welcome to everybody, and we have today the opportunity to have a webinar about an introduction to the in situ thermal remediation. Let's move to the next slide. And all right, here it is. So just for those that are not familiar with NICOLA, NICOLA is a platform for the dissemination, an African forum for the dissemination and exchange of good practices, scientific knowledge, and ideas to manage contaminated land sustainably. We have different working groups on relevant topics, and there is some contaminated land training that periodically is done by some members, and we have also annual conference. It is an opportunity also for networking, where you can develop relationship and strengthen existing relationship with other members of the network. To this purpose, we have regular evening networking events, seminars and webinars like this one, and industry forum events. The scope of NICOLA is to inspire this scientific best practice, stimulating interdisciplinary project collaboration on problems regarding contaminated land, and knowledge transfer to identify needs. It is based on the cooperation between industry, mining, academia, regulator, and service providers, while linking closely to the fields of contaminated land, hydrogeology, geochemistry, and waste management. Planned conference, unfortunately this year, because of the pandemic, we had to suspend it, but however, usually is end of October. So we are planning on October 2021, 28 and 29 in Cape Town. We will have a SUSTREM conference. This will be co-hosted by the Department of Environment, Forestry and Fisheries. The upcoming webinars, just for your information, there will be the next one on the 26th of August, so you can take note about that, about vapor intrusion at 12 in midday. And the presenter will be Steve McQueen from ERM. Also, this webinar is CP accredited. And the following one is on the 9th of September, same time, by Green Soil Group, will be presenting announced by Remediation. So just a quick introduction about this webinar. Is about this in situ thermal remediation. The presenter is Bruce McGee, which I will speak about him later, of Macmillan McGee Group. So GeoStream Group is proud to bring to the attention of NICOLA members this webinar about the latest advances and innovation on thermal technology presented by Bruce, Technical Director and President of Macmillan, of MC2. We make it short. GeoStream Group and MC2 have formed recently a partnership, strategic partnership, to collaborate on thermal remediation projects in Italy, UK, Ireland, Spain, and in South Africa. And both companies are currently working on 2 different thermal projects in Sweden and Italy. The design and implementation of patented in situ thermal remediation technologies are managed by MC2, while Geostream Group contribution to this kind of project is the experience in the design and installation of soil and groundwater remediation system. In particular, soil vapor extraction, catalytic combustions of the recovered gas produced from the degassing process. So let's introduce Bruce. Has over 35 years of experience in the energy and environmental industry, focusing on engineering and technology development of electrothermal process for the recovery of bitumen and heavy oils, as well as remediation of contaminated soil and groundwater. In addition to a strong technical background, Dr. McGee has experience in corporate development, finance, public company directorship, and of course, successful implementation of small to large projects. He's an industry recognized leader in the field of applied electromagnetics and electrothermal heating of soils and oil reservoirs. McGee founded Macmillan McGee in '91 and is the company president since here. He has successfully remediated over 120 contaminated sites in North America, South America, Europe, and Asia, achieving or surpassing non-detected targets using patented processes, which he will explain to us in this webinar. So Bruce, I will pass to you the screen so that you can start your presentation. Thank you very much, Bruce.
Can everyone hear me? Hello?
Yes, thanks.
Oh,
Yes.
perfect.
Hi, thanks.
Good,
Perfect.
good afternoon, everyone in Africa. I hope everyone is safe and healthy. And I'd like to say thank you for the introduction, and also thank you for the opportunity to share. Hopefully, do you see this? Hold on, I'm just going to see if I can move this out of the way. There we go. And I have about 52 minutes, and I think this presentation will take 51 minutes. So we have 1 minute for questions. And I have my background, as you know, is I'm a fairly technical person, and I'm going to take the perspective of this webinar and the introduction to thermal remediation from a science-based approach, and hopefully all the dots get connected with respect to the science, the physics, the math, thermodynamics, and they converge into this idea of using these tools to clean up contaminated sites. And so this might be a little bit of a different approach to presenting a technology for a group of people involved in thermal remediation, but I hope that we have some fun with it. And I also hope that, more importantly, you'll learn a little bit, or maybe even more than a little bit, so that you can somewhat have informed decisions about how you would approach a thermal remediation project from a science-based understanding. But I would like to say a few words about our company. A little bit has already been said, but we're headquartered in Calgary, Alberta, Canada. In developing our business platform, we really took an approach that we wanted to control the technology. We wanted to always improve the technology. We wanted to control the manufacturing, and we wanted to provide the technology to the industry in a way that maximizes the value for both our company and for the project and the client. So we've done many projects in the environmental industry. We're very proud of some of the, hello, to someone, We're very proud of some of the successes we've had. We've done the largest project in the world. We've also completed a project in China, which is a massively huge market for in situ thermal remediation. We, as a Canadian company, we received the largest sole source contract from the United States Department of Energy, and also presently, as far as remediation contracts go in the industry, we were awarded a very large one recently, and I believe it to be the largest remediation contract, thermal remediation contract, two of the vendors. So when we talk about a business platform, we manufacture all of our equipment. We manufacture it to the local jurisdiction standards. And we're also very, very focused on technology. We invest 20 to 25% of our revenues back into research and development. We're constantly involved with universities, and we hire interns throughout the course of the year. And we have 3 laboratories within our facility where we're constantly having fun playing with technology, learning new things, and bringing these learnings to the industry. We have a culture in our company where we do the math. If we don't do the math, we don't do our job. As far as the energy space sector is, we're involved in producing bitumen from the oil sands. We did own oil sands leases, approximately 1 billion barrels of bitumen in place. We recently sold that to a Chinese company, and we will be using the ETDSB technology that I'll be talking to for producing bitumen. So we are positioned globally as a company with a global market. The environmental industry, of course, is an issue around the world, and we're positioned in countries where we see rapid growth. And you can see from the slide here, we're in South America, Australia, we're also North America, Europe, and Asia Pacific. We're really looking forward to what kinds of opportunities we can work with GeoStream in Africa. We've been talking with some companies in Africa on some really exciting environmental projects, and we're looking forward to further discussions. So all of this started a long time ago, and my mentor and PhD supervisor, Dr. Vermeulen, and his group were using electrical heating to heat the oil sands so they could produce the bitumen and, of course, provide an energy source for the oil and gas industry. They used the idea of electrical heating to replace mining back then, a long time ago, as a way of approaching the production of bitumen with a more environmentally friendly technology. So I got involved in this group in 1981 and did my master's degree in electrical engineering with this group, and did my PhD in engineering physics in this group as well. So I fell in love with this idea of being able to produce bitumen using this very interesting technology. But along the way, we somewhat got sidetracked with a group out of the University of California, Berkeley, and they were doing an environmental project in Lawrence Livermore Labs. And they asked us if we could take our technology that we use for producing bitumen to remediate a contaminated site at Lawrence Livermore. And to be honest with you, I had no idea what an environmental industry looked like or would look like. But the idea of putting electrodes in the ground next to clays that were contaminated with benzene and heating them up and extracted them was a curiosity that I just couldn't turn down. So I got involved with this project as a very, very successful project. We removed about 95% of the benzene chemicals from the soil, and we used, it was a very small project, we used electrical heating in combination with steam. And I can tell you, being involved with the project, that the cost of producing a molecule of benzene was about 20%. Using electrical heating was about 20% the cost of producing it with steam. So really successful project. And it launched, a company launched McMillan McGee, pushed it in a direction to provide electrical heating or thermal remediation to the environmental industry. I'm going to try next to show you a little video which will walk you through our technology and also bring out into your perspective some of the features of in situ thermal remediation, and I'm hoping that it works.
Our first project, a large creosote site. The site is characterized by complicated geology with multiple layers of varying lithology. Each lithology has its own unique hydraulic, thermal, and electrical properties. The soil is contaminated with over 50 different chemicals. The contaminant distribution in the soil is even more complex than the geology. The heavier than water chemicals migrate through preferential pathways until their movement is obstructed by clays or an underlying aquitard. Chemicals that are lighter than water will migrate to the water table and accumulate there. So many different chemicals so randomly located in the soil makes it impossible to remediate using conventional multi-phase extraction technologies. Without the help of heat, we know that it can take years, decades, or centuries to reduce the contaminant mass in the soil. We need heat to treat. Heat helps mobilize the chemicals in the vapor and liquid phases. The heating technology of choice is ETDSP, the electrothermal dynamic stripping process. Once the treatment volume boundaries are known, ETDSP begins with a conventional rig, drilling vertical well bores to the bottom of the contaminated soil. Multiple electrodes are lowered into each well, strategically placed next to the contaminated soil. Extraction wells are drilled and connected to conventional surface facilities for the treatment and disposal of the extracted chemicals. Temperature sensors are placed extensively throughout the treatment volume to monitor the progress of heating and optimize the use of energy. A vapor cap provides thermal insulation, controlling fugitive emissions and optimizing chemical vapor extraction. Power delivery systems equipped with advanced internet-based computer control are used to evenly distribute electricity and water injection to the electrodes. A basic electrical resistance heating system typically has one electrode in a wellbore, limiting the capability to optimize heating of complex geology and control currents from taking the path of least resistance. Neutral currents can stray into the grounding of other electrical equipment, causing potential safety hazards. Convection is not implemented, reducing efficiency and uniformity of temperature. Extraction at electrodes removes heat where it is needed most. Conduction heating is a very slow process, and without convection can cause overheating at the electrodes. ETDSP implements all the heat transfer mechanisms. Time-distributed control ensures electrical energy is evenly shared between all electrodes. Interface synchronization ensures uniform electrical heating in complex geology. Proprietary grounding makes sure every electron is accounted for, so that stray currents do not interfere with other electrical systems or infrastructure. Overheating at electrodes is solved by injecting water using a balanced and optimized strategy from computer-controlled water circulation systems. Just enough water is injected to ensure maximum convective heat transfer and also to preserve the energy balance. Electrodes are sophisticated electrical components engineered to provide the heat transfer solution fundamentally needed for thermal remediation. With ETDSP, all the heat transfer mechanisms work together in synergetic proportion to achieve uniform heating. The electrothermal dynamic stripping process reaches the desired results more rapidly and evenly than any other in situ electrical resistance heating technology. With heat comes tremendously accelerated mass extraction. Vapors are generated, fluids flow with less resistance, chemicals are desorbed and dissolved, water turns to steam and strips away the chemicals. The permeability of the soil is greatly enhanced with increasing temperature. Extraction wells with properly designed well streams operating under vacuum pull the vapors and liquids rapidly from the soil, leaving the silt and sand material behind. The ET-DSP system, operating with a conventional multi-phase extraction system, in effect compresses the operating time to reach desired remediation goals from decades to months. There is little room for miscalculation. Everything has to work together in real time. We do the math first. We operate in the solution. We make operational decisions using real-time data, which we share with our clients, so that progress of a project can be monitored in an honest, transparent, and cooperative team environment. An engaged team of professionals working from the same page is key to the success of a project. No remediation project is too small or too big for our team. We have worked on the largest in-situ thermal remediation project in the world to small source zone reduction programs. Let the electrothermal dynamic stripping process, our ET-DSP technology, be the technology of choice for your thermal remediation needs.
So thank you for hopefully that video worked for everyone. So let's have some fun with math and physics. So first, these equations that you see here tell you everything there is to know about in situ thermal remediation when it comes to heating the soil. In fact, if you can solve all these equations, you can have my job. And when we look at these equations and we take a deeper dive into them, we learn a lot about how to design an in situ thermal remediation system, how to choose an in situ thermal remediation, and how to best operate an in situ thermal remediation so that we can optimize heat losses, energy usage, and maximize the value. So let's take a look at some of what we've done at McMillan McGee to investigate the physics of these processes in order to understand the in situ thermal remediation of soils and address some of the concerns that come out of looking at the science and the math and the physics in detail. So one of the first things we want to look at is this idea of a finite length electrode. And again, we put electrodes in the ground, we put them beside the soil, we pass current from the electrode into the soil, and we hope that we achieve a really beneficial result. But the question is, can you actually do it? And so one of the things I looked at was taking an electrode, putting it in the soil, giving it a finite length, and asking, what is the electric field around that electrode? Because that's what's going to heat the soil. And from there, try to understand what is the power density distribution. Now, notionally, you would just think that you could put the electrode in the ground and turn it on and you're going to get your desired result, but it's really, truly not that simple. So what I've done here is I've taken a finite element model and I've used a huge amount of nodes in the finite element model to model the physics of this equation that you see on the screen, which is shown earlier, which is the heat transfer equation. And it's also coupled with an electromagnetic equation, the heating equation from electricity. And we're going to ask ourselves, what is this power density distribution from the electrode? So I've got a quarter electrode shown there just because of symmetry. So I didn't have to wait forever for the solution to be produced. So let's start with this understanding. So let's solve this electric field. And from this electric field, let's find out what this power density distribution is and see if we can learn anything about how to use this electrode to heat the soil. So the first thing we want to do is look at this voltage distribution. The voltage distribution around the electrode is going to lead us to the electric field, but we need to first calculate the voltage distribution. When you look at it, you see the color contours around the electrodes show that it's a fairly nice uniform distribution of voltage, but the truth is the voltage isn't going to give you the calculation you need for the power density. What you need is a calculation of the electric field. So most people would probably stop here and be happy with the result and move forward with the notion that a finite length electrode is not a problem. And in fact, we can just proceed as initially expected. But let's calculate this electric field. Now, the electric field is just the derivative of the voltage. In other words, the electric field is the voltage gradient. So let's look at what that looks like. So we calculate the electric field and we see something that is a little bit more of a surprise. We see that most of the current is leaving the end of the electrode. And why is that? Well, you've got this piece of steel on the ground and it's made out of a very conductive material. And at any moment in time, the voltage on that piece of steel is uniformly constant. So all these electrons are trying to move away from each other because though opposites attract, like charges repel each other, and they're trying to leave the electrode away from the center. So you see this electric field having intensity at the top of the electrode and less in the middle of the electrode. In fact, it's almost a ratio factor of 2. But we haven't solved the power density distribution problem yet. We now have to take the electric field and more or less square it, like power equals I squared R. So you got to take this electric field and square it. So now let's look at this power density that we have, that we've created around the electrode. And we see it even looks a little bit less attractive. It's most of the power density occurs at the top of the electrode. In this slide, of course, it'll be replicated by symmetry in the bottom of the electrode. So you have this finite length electrode, which initially you thought would just be something that would be useful and easy to use, that comes in and introduces an engineering issue. In other words, all the power density is near the top and bottom of the electrode. In fact, it's almost a factor of 4 of what you would expect. So that's a concern. And also we know that the electric field falls off, the power density falls off dramatically as you move away from the finite length electrode or any electrode. It falls off as 1 over R squared. So you got this issue of a decreasing power density away from the electrode, even if it was infinitely long. And then you've got this accumulation of power density at the top and bottom of the electrode, which can be described by physics and be calculated by math. So let's see what this when you take this solution and you put it into the heat transfer equation, what kind of temperatures can you expect? And here we go with this calculation. You see this finite length electrode, and you see what's happening is the top and bottom get really hot. And they get so hot, they boil off the water. And if you don't have water in the pore space, you can't conduct electricity. So one of the things we did by addressing the physics is we introduced an electrode design where we could inject water into the top and bottom of the electrode, catch that power density, and force it into the soil so we could get effective heat transfer. So this is a design of an electrode, our electrode that we use. You can see that it's got a hose going to it. It's got an upper and lower ballast, which has injection ports so that it can pick up that energy that accumulates and is most dense and transfer it into the soil. The other thing here is that it seems that the longer you have your electrode, the less efficient it's going to be, or the less controllable it's going to be. So having a number of finite length electrodes allows you to heat uniformly and create these temperature distributions, which are incredibly, provide an incredible thermal result in the soil. And in fact, with these finite length electrodes, you can put them around a treatment volume and you can heat up the soil that you want to heat up really almost surgically and get your desired heat transfer problem. But we are dealing with electrodes, and so we're passing current through the soil. And some people are afraid of heights. I'm afraid of electricity. I'm really concerned about what happens when we're implementing an ETDSP process in the soil. So we calculate this electric field, and what you're seeing here is one cycle of a sine wave as it's connected to a number of different electrodes in the soil, and we're watching where the electrons go. And with our approach, and with the approach that is the most safe, is that you want to capture every single electron that you introduce in the soil so that no one else. So is the capture of these electrons. Another thing you'll see here on the right-hand side, psychedelic colored light, is the voltage distribution. You will see away from the electrodes that the gradients there are effectively zero by virtue of the fact that we've separated the utility ground from the ground that we use to reference all our potentials, and we call that our ETD neutral. So you looking at the physics and math, we can pull those things together in a way that makes it a safer system to operate. So now let's look at soil. Soil is a rather random physical thing. And geologists will tell you this, that, you know, if you move 1 meter, 2 meters away in the soil, the properties are going to change. So it's really important for us to understand one of the properties of the soil, which is the electrical conductivity. And what I'm showing here is a slide that shows the variation of electrical conductivity as a function of water saturation and also as a function of temperature. And what you'll see here is that during the normal operation of an electrical resistant heating process, the electrical conductivity can vary by 2 orders of magnitude. That's amazing. So some of your electrodes are going to be in really high conductivity zones, and some of them might be in zones that are less conductive. So those electrodes that are in really high conductivity zones are going to draw more current. And in fact, they may draw more current than other electrodes, and therefore create a scenario where you're not going to uniform. Yeah.
Bruce, can I interrupt for a second? There seems to be somebody that's speaking in the background, or there's some interference, and we're missing every other word that you're saying. So if we could ask everyone to go on to mute while Bruce is talking, would be much appreciated. Try again, Bruce. Thank you. Sorry for the interruption.
Okay, thank you, Brent. So every electrode will now have a different resistance, and this creates a situation somewhat like the weakest link in a chain. The electrode that uses the most current robs current from other electrodes, and because frankly the power supply only has a limited amount of current, and you're going to have a scenario or an issue where you're going to have hot spots in your soil because of this non-uniform distribution of current that's caused by this incredibly heterogeneous soil, and that property shows up as the electrical conductivity. So what you have to do is come up with a process where you can control the power to each electrode, and this is something we do with a concept that we developed called time distributed control. So we can make the issue of variable geology a non-issue. The other thing we talk about is this idea of conduction heating. Now, conduction heating is basically transferring energy from a heating source into the soil, but there's no power distribution in the soil. All we're relying on is this idea that there's great temperature gradients associated with the heat source. So the heat source gets up very, very high temperatures, and it transfers heat to the soil through those temperature gradients. And you can see that by the simplified equation. So, but we still have soil properties that we have to really be aware of. And this little video here is going to show you what can happen when we simulate the temperature distribution away from really high temperature heaters, and we've got multiple thermal conductivities within the soil. Now, this is actually a pretty simple calculation. We take into account the change in thermal conductivity with water saturation, temperature, and geological type, lithological units when we do the modeling, so we get a lot more of a realistic calculation. But this calculation shows you well enough that you got to understand the geology so you can know the physics to do the math to come up with a solution for your temperature distribution. And in this case, we didn't do that. This calculation didn't do that. And here you have to really look at controlling that temperature at those heater wells so you can overcome the variability of geology. So let's look at some pore level physics. Now, this is some work I did, Dr. Shute and Dr. Vermeulen, University of Alberta, and myself did, where we looked at some of the mechanisms of heat transfer and behavior of an electric field in the porous media. And the first elementary thing to consider is that current actually doesn't flow through the soil. It flows through the water in the pore space. And what's really interesting is that you get a charge distribution around the soil grains and around the between the water and the chemicals, which results in a lowering of the interfacial tension. And we found for bitumen that reduces the residual saturations of bitumen by a factor of 2 to 4. We think it helps in thermal remediation, where some of the chemicals have very high interfacial tensions. And by having an electric field there and having a charge distribution that presents itself on the surface and the boundaries of the water and the chemicals will change that distribution. The other thing is there's a mechanical force that's going on when you're boiling water in the pore space. It's going to change its volume, it's going to change its shape, it's going to move around, and anybody who's watched water boil on a stove, in a pot on a stove, can see that there's a lot of mechanical action going on. So this mechanical action at the pore level is going to move things around, and it's going to move things out of the pore system into other pore systems in a rather random way, but in an actually rather positive way. And the other thing that it's going to happen is because of pore pressure, especially in clays where the confining pressure is very high, you're going to have these microfractures. You're going to change the permeability of the clays and soils a lot with thermal heating. And this is a sample of clay we dug up out of the soil after heating it on a project we had with Shell Oil. And we were just amazed at how different it looked than a normal piece of clay. The other thing we wanted to focus on when we're looking at the math is we don't want to put in more energy than we need to. So once you boil water, it gets to 100 degrees C, and any more energy you put into it is just taking that water and putting it in steam. So there is a balance between how much steam vapor you want and how much energy you want to put in the system. And we believe that we only want to create as much steam as necessary. And for those out there, our rule of thumb is about 6% of the water in the pore space should be converted to steam. Any more than that, and you're going to be paying for the energy with very little value. So what did we learn? Here we learned that physics and math matter. They can point you in the direction of calculation for design of an in-situ thermal remediation project. You can calculate energy input and your heat losses. You can address geological issues and concerns, come up with the right spacing so you get everything hot. And you will be able to produce from the temperature distribution, your mass recovery curve, your water balance, and also play around with other designs to do some optimization. So let's move a little bit into thermodynamics. Now, thermodynamics is a really important issue because when we're talking about taking chemicals that are in the ground in the liquid phase and getting them to the surface and reducing their presence in the soil to numbers like 99% mass recovery, the only way you're going to do that is to turn those chemicals into vapor. And that's all about thermodynamics. So typical project, you're going to produce 1,000 times more vapor than you're going to produce liquid over the life of the project in terms of its pore volumes. So if you're going to be dealing with, or you're going to be looking at an in-situ thermal remediation technology for your project and for your chemicals, you need to know the thermodynamics, the thermodynamic behavior of the vapor. And here's a really simple example. A lot of projects we deal with are around chemicals like TCE and PCE. These are DNAPLs. You can see that the TCE will boil at 87 degrees Celsius, which is nice because an electrical resistance heating technology only goes to the boiling temperature of water at the saturation pressure, which is around 100 degrees C, which is right here. And then you get something like PCE, and it boils at 121 degrees C, but you have something working for you. And it's called the co-boiling temperature. And here you can see that PCE in the presence of water will boil at 88 degrees C, and TCE in the presence of water at 73 degrees C. But once you get those chemicals into the vapor phase, you have a duty to produce it. So here's a lot of chemicals here. You can see everything above the red line will be in the vapor phase at below, at or below 100 degrees C. Those chemicals to the right that are below the red line, these chemicals typically can be stripped out of the soil, or you're just going to have to address them with a higher temperature technology like conduction heating. So like I said, once you get these chemicals in the vapor phase, you have invested a lot of money, a lot of time. There's been a lot of logistics and infrastructure put in place. You want to take the really smart approach to getting them out of the soil. And that's your duty, that's the job of remediation. So we looked at this, and it was not an easy problem to solve. And I worked with the Pacific Institute of Mathematical Sciences. You see a lot of really names there. These people are PhD mathematicians from around the world, MIT, Caltech, universities in Canada and the US. And they get together every year and solve industry problems, and they've solved 5 of them for us. We sponsor this organization. And we came up, I brought this problem to this group and said, look, at how do we look at this idea that you've got a liquid phase NAPL, it's a DNAPL, it's sitting at the bottom of a contaminated soil, how do we get it out? So we basically looked at trying to describe this problem. So you have this molecule of hydrocarbon, and it's just sitting there, and you're putting in extraction wells. And we have this idea of this radius of influence, that if we draw down hard enough on this extraction well, we're going to move that molecule over towards it. And so that's what we see here. But when we start to heat up, we introduce this new force called buoyancy. And this buoyancy is going to, especially if this little molecule of DNAPL turns into a bubble, it's going to want to float up. So you have this buoyancy force acting upwards, and you have this force that's created by the pressure gradient from an extraction well, and it's trying to capture it. It's trying to grab it in. So we came up with this new concept called radius of capture. You got to get this bubble. And we're going to put some conditions around what it takes to get that bubble. And a condition we put around it is we want to get that bubble before it leaves the heated volume. So it's flowing through the treatment volume, but we want to get it before it leaves the heated volume and becomes a liquid again. So we came up with these calculations, this math, you can download the paper. We came up with this radius between the extraction wells, and we were able to have a design approach for getting these bubbles. I have since then used some of those equations into a little analytical model, which I hope to present as a poster. It gets pretty good results. There's the black dot in a curve of the analytical model showing some real field data, but it doesn't take into account all the physics. So let's just look a little bit more at the physics. I said, okay, well, I'm going to use this physics model and look at clay lenses. I'm going to drop some TCE on the surface and model it for 10 years and see how it finds its way through the soil. And of course, it's going to land on those non-permeable surfaces. After 10 years, I'm going to assume we're pretty close to steady state. I'm going to go in there and I'm going to heat that soil. In this case, I'm using electrical resistance heating. I'm going to heat it all up. And I want to know, what does the mass transfer look like? So I've got these thermodynamic equations in here, and I got this contamination sitting on those clays. What does it look like to extract out of the soil? So I start extracting almost immediately when the project starts. And what we're going to see here is the saturation of the vapor phase, the saturation of the gas phase. And you can see when it's starting things are starting to go into vapor phase. And you can see they're coming out of the extraction wells. And you can see that as I turn this into vapor, I'm getting really successful extraction from the vapor phase. But what's really interesting is almost all of the vapor is coming out within the heated volume. So within the heated volume, we really believe that you've got to extract outside of the inside the heated volume. Some of it does find its way above and come out, but for the most part, all of the vapor extraction occurs within the heated volume. I know that sounds intuitively obvious, but until you do the calculation, it doesn't quantify. The obviousness isn't quantified. So here's the mass recovery curve I got from that simulation. Here I got about 93% of the mass out. This was a TCE chemical, as I showed you there earlier. One of the things you can do, which I didn't do in the simulation, is start pulsing. So just start extracting aggressively harder at other wells and less at other wells, and sort of shake things up like you would if you were shaking up the soil. And what's kind of nice is when I did this model and I just said, okay, look at the shape of that curve, and I compare it now to the real field problem. I don't know if it's good luck or dumb luck, but it looks pretty close. So the thermodynamics. So when we look at this thermodynamics, we can't help but emphasize we've got to vaporize stuff. You know, some of the things that are working in our favor are the dynamic stripping. You've got this mobility improvement, and some of the things that people talk about, which I think are true and which are probably useful, are enhanced bioremediation through thermophilic processes, and this idea of hydrolysis, which has to do with the breakdown of chemicals as they get hotter with water. So lessons learned: design the extraction and treatment system based on the thermodynamics of the chemicals of concern. Extract from the heated volume and design your extraction rate for 5 to 8 pour volumes per day. But don't forget, heating and treating must work together. If you extract too much, you're pulling out too much energy, you're failing your heating system. If you don't extract enough, you're going to lose your chemicals outside your treatment volume and you're failing your remediation process. So let's talk a little bit about thermal remediation. Well, thermal remediation is a holistic approach to cleaning out contaminated soils. We rely on really smart consultants who know the sites, have done conceptual site modeling, have defined the treatment volume. We rely on the site assessment model. It's our contractual. It becomes our contract to do the remediation, and we go through this logical process of even determining whether thermal is needed. But every step of the way, we do the math, and we kind of look at everything and say, well, what's the right technology to use? And I've got this little tiny decision tree here. You know, what's the volatility of the chemicals? Are they in clays? Are they in sands? And how thick are they? Is there really high conductivity? Is this site resistive enough to pass current through? Is there a hydrogeological issue with groundwater flow? What's the cleanup goal? If there's a really stringent cleanup goal, do we have to design for that? So all of these things come together in a very holistic approach where it's a real team effort between companies like us who provide the technology and consultants and clients who really know everything, a lot more about the problem than we could ever hope to know. And of course, based on that, we can bring in the different types of options for in situ thermal remediation, steam, underground dynamic stripping, combinations of all of these, in situ thermal, conduction heating. And you can build a matrix, and this is a matrix that was presented at one of our symposiums. And you can build this table of evaluations where you put in those factors like geology, soil properties, hydrogeology, chemicals, types of chemicals, and you just sort of go through and you build a matrix that gives you some sense of your decision-making process. Let's talk a little bit about some of our projects. We're very, very proud of some of these projects, actually all of these projects. And let's just talk about some ETDSP projects. Here's one that we did at a university in Boston. It was a land transfer project. We had to remove the chemical contaminants before the property could be transferred to the buyer of the property. It was a $25 million remediation project resulting in a $500 million land transaction. And you can see where the electrodes are located. This is in a construction phase. The next project I'm going to show you is in Brazil. And the other project I want to show you, we've been in the developing this high temperature technology we call ITDSP for the last 5 years. It's a plug and play technology that plugs into our existing technology infrastructure. The great thing about it is we get to temperatures that are really, really hot when it comes to dealing with contaminants that are difficult to boil off at the temperature the water boils at. Sorry about the noise. It's basically an inductive heating technology. You see the coil coming out of the heater well. We produce an electromagnetic field on the casing, and it gets super, super, super hot. This is our test facility in the backyard. We're still heating and testing and coming up with new inverter technology, testing the modeling. It's coming along really good. This is a project we have with GeoStream in Italy using this technology. And this is a project of the technology in Sweden, which is actually the largest remediation project in all of Sweden. You can see there's over 1,000 heater well locations. And this temperature target here is over 300 degrees C to clean up the pesticides on that site. So some lessons learned: design for the peak, thermodynamics, thermal remediation. You're going to have a treatment system. You're going to have a partnership with a great treatment system vendor, and you've got to design that system for the peak. And we don't typically, the peak happens when you get the temperature, and unfortunately it doesn't last the whole project, but it definitely you do not want the treatment system to be controlling the operations. You want the treatment system to be out of the critical path so that you can operate the project efficiently. The second thing that I really advocate is this whole idea of the fact that this in situ thermal remediation is the most powerful technology for cleaning contaminated soils without digging them up. And you're going to spend a lot of money just looking at the regulatory, all of the legal stuff. You're going to spend a lot of money, design and mob and construction. And when by the time you start thermal remediation operations, you spent half of your budget. And when you start, you want to stay on the curve, because if you decide somewhere along the way that you want to try something different, using co-technologies, you're going to start again from the beginning. So our advice to everyone is really do the math up front, make this the best in situ thermal remediation design you possibly can. Make sure you've considered everything, and you're going to have a successful project. One more thing I'd like to say is that we have an International In Situ Thermal Remediation Symposium. This is our third one. We're the host of it every 2 years. This year it's on May 19th, May 20th, 2021. We'd love to see you there. We'd love to see you bring in some of your ideas, submit a paper, and just email me with the details. And I just want to really say thank you. Thanks to our friends at GeoStream, my team at McMillan McGee, and all of you participants who have patiently waited through this webinar. And I am open to questions if you have any.
Thank you, Bruce. So we are open for questions. Just a very quick one. I imagine some of you are waiting for the password for the CBDB points. So the password, if you can take note, unfortunately we cannot put the slide on, but it is blue grapes. So please take note, blue grapes. So let's give space to the question for Bruce. Any question? Well, it looks like everyone is on mute, but you can unmute.
Andrea, there is a question in the chat box.
Yeah. Sorry. Yeah, I haven't seen that. Okay, if it is possible to recover contaminants for reuse in other applications. Recover contaminants for reuse in other applications. Bruce, what?
That's a really interesting question, and I'm going to interpret it that you produce these chemicals out of the ground. Do you dispose of them, or is there something you can do with them other than dispose of them? And we worked on a project with Total where we had so much mass in the ground that we produced truckloads of chemicals. And what we actually did was we took those chemicals and we sold them to a power company that used them to generate electrical energy. So that was one example of where we were actually able to produce chemicals and reuse them. As a general comment, when you go through this process of heating these chemicals and separating them from the soil and the water and other chemicals, you're going through a chemical distillation process. And when we look at the chemicals as they go into the collection tanks or the treatment tanks through the treatment system, they come out beautifully clean and clear. And you can't help but ask yourself, can I sell this to someone? So I think the answer is there's an opportunity to look at that and see if there's value in the chemicals you produce other than just disposing of them. So thank you for the question.
If I could add a little bit to that too, there's been a number of projects that we've done where, just as Bruce has alluded to, we've been able to recover those contaminants, specifically with a carbon regen system. And as Bruce had mentioned, you can decant these in the pure chemical phase, and we have recycled those contaminants, specifically chlorinated solvents like TCE and PCE. We have sold those recovered chemicals back to recyclers who can then bring it back into use. So yes, it can be done. It very much depends on the jurisdiction that you're working in. Some places require us to destroy the chemicals in situ or right on the site, but in other places we can remove them and either take them away off site for disposal or for reuse.
Thank you, Brent, for adding to the answer to the question. I have another question here in the chat room, which relates to a ballpark cost of producing for remediating a contaminated site. I'm going to say, I want to rephrase the question just a little bit, and I'm going to give you a ballpark cost in North America with North American numbers. I mean, there's an advantage some places around the world where things are cheaper, and sometimes even a disadvantage where things might be more expensive. But if you sit back and say, okay, I am on a big project, by the time I get through all of the costs from the start to the finish of a thermal remediation project, you're looking anywhere from $150 to $200 per cubic meter of soil that you treat, US. If you're using a lower temperature, and I use lower temperature, I refer to something like steam or ETDSB or electrical resistance heating. If you're dealing with really, really high boiling chemicals where you have to get a lot hotter, that price can increase by about $50 per cubic meter to numbers like $200, $250 per cubic meter. Brent, would that be approximately accurate?
Yeah, I would agree with that. And the cheapest project that we've ever done on a per cubic yard or per cubic meter basis was the one that Bruce showed you, or we discussed with Total in North Carolina. That project was about 250,000 cubic meters in size and was completed for $80 to $85 per meter. Now, when you have a very small project, your economies of scale tend to drift. on that one. So the cost per cube can be much higher than that. But typically, you know, that's a range to go with. $150 to $250 per cubic meter is a all-in cost that would include everything: drilling, electricity consumption, extraction and treatment, oversight, consulting, you name it. Everything would be in that kind of ballpark. Again, those are North American numbers. Projects in Brazil and China and other places have come in even less expensive than that.
Thank you, Brent. One of the questions, very good question about produced vapor and whether or not that adds to the atmospheric pollution of a project. And none of the vapor that's produced, none of the chemicals that are produced in the vapor or liquid phase are released to the atmosphere through the treatment system. They're immediately condensed by the treatment system through heat exchangers, through proper design of designing the treatment system to hit that peak mass, and they're either collected in carbon or they're destroyed in thermal oxidizers. So thank you for the question. Another question here, which is a really good question, what's the impact of high groundwater fluxes on the effectiveness of the remediation process? And it's a negative impact. You get cold water flowing into heated volume, you have to heat that cold water. But if too much cold water flows into heated volume, then you've got to deal with the fact that you might not have enough energy to deal with that cold water. So as a rule of thumb, we did a study for the U.S. Department of Energy, and we went through and said, what are the limits when it comes to groundwater flowing into the heated volume and actually compromising it to the point that we can't achieve target temperatures. And the number we came up with, and through the calculations and the modeling, was about 3 to 4 feet per day of groundwater flow velocity. In that case, you have to do things in order to block that water or prevent it from entering the treatment volume. And we presented a paper 2 years ago at Battelle, or the last Battelle, I can't remember what it was, where we addressed specifically those issues and those possible solutions where you might want to put up a barrier wall, where you might want to put up upgrade steam injection or upgrade extraction to counter off the groundwater flow. Excellent question. It is an issue, and it definitely has to be dealt with in the design phase of a remediation project. Thank you for the question. So I got a question. What is the average duration of a thermal remediation project? So we typically budget for 6 months, from the start of heating to the end of heating for a remediation project. There are things you can do to reduce the activity in a project during that time, and maybe even close out the project before the 6 months is up. One of them is to do interim sampling. So if you're 4 months into the project and your extraction wells look like they're not producing any more chemicals in it, all the lines of evidence are suggesting that certain areas of the project are clean. You can go in there and sample. And if the sampling shows you that you're clean, then really there's no reason to continue heating there. So you can turn off parts of the system and focus on other parts of the treatment volume that still require remediation. So I think that some of these projects go longer because sometimes the site isn't properly characterized, sometimes it's bigger, we have to expand it. Sometimes we find a new chemical that wasn't discovered in the first place. So good question, but there are ways to manage the duration of a project.
Thank you. Okay, looks like there are no more questions out there. We thank you very, very much, Bruce and Brent, for the presentation and the participation to this NICOLA webinar series. I hope that also this webinar has been interesting to all the audience. More than 65 people were attending. So thank you very much again, all of you who connected, and we look forward to the next webinar. Thank you very much to everybody.
Thank you very much, and stay safe and play safe. Talk to you soon.